Hello, everyone. Thank you all for being here today. And I wanted to start out by thanking the Indaba organizers for letting me, in particular, speak at this conference. Because I can guarantee you that I know far, far less about machine learning than anyone else in this room. I'm an ecologist. I study animals. I think about animals and what they are and what they do. But I'm very fortunate to work with people who do have an extensive knowledge of machine learning and who are willing to put that knowledge to good use. And so I'm here today as a bit of an ambassador for ecology and conservation, here to talk about the challenges that we face trying to understand African ecosystems, and trying to really highlight some specific opportunities for AI to step in and to work for social good and for scientific discovery and for conservation in this framework. So as a biologist, what we're interested in having artificial intelligence help us do is to really make new scientific discoveries in the fields of ecology and conservation, to facilitate coexistence. These are old slides, these are backwards. Find new ways to facilitate coexistence between humans and wildlife, and to really have a big impact in terms of saving wild species and wild spaces. So I'm just really going to be setting the stage for Stig's part of the talk, introducing you all to some of the questions that we biologists are asking right now regarding African ecosystems, talking about conservation in Africa, talking about how we've historically gone around collecting the kinds of data that we use to answer these questions, and how that process has changed with new advancements in technology. These changes have brought along concomitant challenges, which are, again, those opportunities where we really feel like AI can step in and help us start making new advancements in these areas. So first of all, what are the phenomena that biologists are interested in studying? What are the core issues that we're trying to tackle at the moment? So from the science point of view, what we're really interested in doing is understanding these very complex animal communities. We can then use that knowledge and apply it to conservation efforts and to help promote these initiatives that allow for human and wildlife coexistence. So it continuously amazes me really how much more there always is to understand about wildlife community dynamics, especially here in Africa. Africa has some of the most biodiverse ecological communities on the planet, as well as some of the last remaining pristine ecosystems on the planet. So we're very interested as biologists in understanding what forces allowed this kind of diversity to be generated and how we're able to have so many different species of animals coexisting in the same landscapes. With the unparalleled diversity comes along unparalleled complexity, and you can only imagine how difficult it is to try and untangle all of these very complex interaction networks to figure out all of these different relationships between animals and among animals, or among animals and between animals in their environment. The role that an animal plays in their environment, their position in that complex interaction network, is largely dictated by their behavioral traits. So behavior is hypothesized to be a strong force shaping wildlife communities and contributing to their resilience. But we're still really trying to understand which of these different behaviors is really important and why that might be. Finally, these animal communities, they're not static. They're shaped by how their landscape changes across space and through time. So spatial heterogeneity dictates not only what animals are able to live in a landscape and in what abundance, but it also affects how animals move through these landscapes and the kinds of interactions and trade-offs that they face as a result. The landscape itself, the spatial distribution of resources and predation risk and competition and disease, this changes dynamically through time. It can change hourly, daily, monthly, seasonally, or throughout the year, and these temporal changes then also shape how animals interact with these wild spaces and with each other. Animal behavior and their demography, in turn, going down the next level, modulate how and how strongly these animals impact their environment. So if we're interested in understanding ecosystem processes like carbon sequestration, like oxygen production, fire regimes, nutrient cycling, water potential, among many others, we really need to know how these higher trophic levels, how animals contribute to those different pathways. So in addition to these very basic biological questions, we're also very actively and very urgently testing theories that improve our ability to forecast how humans are affecting wildlife communities and to help us develop solutions to promote human-wildlife coexistence. So we very urgently need to understand what anthropogenic factors are contributing to species population declines and range shrinkages. Why is this happening? What species are susceptible? How and how quickly are their populations declining? If we're not able to save a species, either globally or locally, what happens when we remove that player from this interaction web, or we change what these relationships look like? Changing those relationships could lead to these cascading effects throughout entire ecosystems. We still don't really know how changing animal behavior or demography is going to trickle down and affect all of those ecosystem services that we rely on. And of course, changing wildlife dynamics can have more direct impacts on human well-being as well. As we encroach further and further into wild spaces, we increase our interactions with wildlife. And then these wildlife dynamics can be very detrimental to human livelihoods, such as through crop raiding, and even in very extreme cases, directly to human lives. So what we're doing, like the science that we're doing, is really trying to mitigate these negative interactions, promote positive interactions, find ways to increase the well-being of both humans and wildlife in the same spaces. So for example, a lot of the work that I do in my professional career is really aimed at restoring degraded wildlife systems and in maintaining the correct ecological processes in preserved natural areas. So a lot of what I do is studying wildlife reintroductions, anti-poaching strategies, different adaptive management regimes, and using the science to assess and inform those conservation efforts. So I've just thrown like a very large number of questions and themes and ideas and things that we're studying at you. But the one commonality among all of these different research threads is the kind of data that we need in order to start chipping away at these questions. So in order to study wildlife dynamics and how humans impact those dynamics, we need a very good understanding of animal abundance, of animal distribution, and of animal behavior. And because a lot of these processes that I've talked about, they don't necessarily occur on very local scales. They occur across reserves, they occur across landscapes, they occur across countries and continents across the world. Ideally, what we would love to have is very high-scale, high-resolution data collected across vast spatial and temporal scales, and again, ideally on entire animal communities. So collecting this dream data is a little bit difficult through the traditional methods that we use as ecologists. So ecological research, typically what we do is we choose one very abundant animal, we look at it in one specific area, and we do it for a short period of time. And that really limits our ability to draw inference on some of these larger scale processes. So while we still do research like this, and we still value research like this, like I still do a lot of research like this, the growth of technology has really opened up these new opportunities for us to start looking at these ecological processes across broader scales while still returning like really high quality information. The growth of technology has also allowed us to collect unprecedented amounts of data, which opens up again these opportunities for us to ask questions that before we wouldn't have even had the statistical power to address. So the kinds of sensors that I'm talking about, remote sensors, in situ sensors, the kinds of data that are particularly valuable for ecologists and for the kinds of work that I do is image data. So whether that's data collected from space by satellites, from the air by drones, or from the ground by remote cameras, these images contain a lot of that information that I talked about as being really specifically important for asking these kinds of questions. So I'm going to zoom in now on the camera trapping, which is my area of expertise and the focus of this current research. Camera traps are remote cameras. You deploy them in the field, you leave them there. They're triggered by heat and motion to take pictures of passing wildlife. And so while it sounds like a very simple tool, the ability for these cameras to collect data 24/7, the fact that we can put them anywhere, we don't have people around influencing animal behavior, all of these factors make them an incredibly valuable tool in ecology. They really allow us a glimpse into the secret lives of animals that has never before been possible. So the kinds of data that we get out of a camera trap image, we obviously get a picture, or in some cases a video, of whatever animal triggered the camera. We know when and where that picture was taken. In some cases, we can actually individually identify the animal in the image, and we also end up with a permanent record of that animal's behavior. And so with the advancements in technology and the cost of camera traps going down, it makes this tool very amenable for these kinds of large-scale, long-term biodiversity monitoring surveys. And these surveys have a great data gathering potential. So what I'm talking about is deploying cameras across entire landscapes, which allows us to collect baseline data on how animal community and population dynamics vary over space. But then if we run these surveys across months and years, we're able to see how animal decision-making and movement and population trends change through time in response to different kinds of temporal cycles and perturbations. So this, for example, is from one of my camera trap grids. Each circle is a camera trap. The circles are scaled by how many animals are there. And every month, you can actually track the Serengeti Mara migration traveling through our field site. And the final thing about the cameras is that they don't discriminate. If you put a camera trap out, it's going to collect data on your entire ecological community, not just one specific species. So I work with a lot of camera trapping projects across Africa. I'm just going to highlight quickly some of my favorite projects and talk about how we run them and the kinds of information we get out of them. Our flagship project, and some of you may have been working with this data this week, is called Snapshot Serengeti. We established this in the core of Serengeti National Park back in 2010. Using just over 200 camera traps, we're monitoring an area of over 1,200 square kilometers. And with almost a decade's worth of data, we're able to look at how animal behavior and how animal populations change through droughts, through El Nino years, as the park becomes increasingly encroached from the outside, with the addition of roads and other linear infrastructure, as poaching becomes more prevalent. But we've also been able to use these data to ask some really exciting biological questions, such as how we're able to have such complex carnivore communities coexisting, and some different facets of predator-prey dynamics. Another project that I really like that we're working on at the moment is in Mozambique, in Gorongosa National Park. Our Wildcam Gorongosa project was started in 2016. This is 60 camera traps covering about a fifth, a sixth of the park. And what's super fascinating about this site is that it was completely defaunated during a recent civil war. So it went from being this gorgeous biodiverse gem of Africa, safari destination location, to having essentially no wildlife whatsoever. So we're using this camera trap grid in part to track the reassembly of this animal community, how these animal populations recover, how our recent predator reintroductions are changing animal behavior. This site was also hit by the recent cyclone Idai, so the worst tropical storm to hit the east coast of Africa in 100 years, smashed right through our field site. So again, we can use the cameras to track how animals respond to these kinds of natural disasters, which is particularly important as these severe weather events are predicted to become more and more frequent with climate change. But these are just two of many projects that I am associated with, which is just a handful of the camera trapping projects in Africa and across the globe. The focus of these projects ranges from purely biological to strictly conservation focused, and a whole gradient of questions in between. But again, the commonality among all of these projects is how heavily they rely on the image data gathered by their camera trapping networks. So having entered the world of big data in ecology, this has of course brought up a lot of big challenges. And the biggest challenge for us working with camera trap data is how we take an image and turn it into numbers. I can't crunch images, I crunch numbers. I can't do my analyses with the kinds of data that we return from the field. So again, the kinds of data that we want from a camera trap image, on a very basic level, we're interested in what species we find in that image, how many individuals of each different species there are, and then what they're doing, what each of these animals is doing in the picture. So I once sat down and calculated how long it would have taken me, a graduate student, to classify a year's worth of data from our Serengeti camera trap grid. So our Serengeti camera trap grid, 200 cameras, maybe like a medium to large size project. A year's worth of data is almost 700,000 images. So if I worked full days, and I never took weekends, and I never took holidays, and I never got sick, and all I did was classify camera trap photos, it would take me 1.3 years to classify that data. It would take me more time to classify the data than it took to collect the data. And this is just turning the pictures into numbers. This isn't even then all of the analyses that I have to do on that data to actually get something out of it. So sicking graduate students at the problem is not the solution. In the past, what we've relied on is citizen science. So we've essentially crowdsourced the classification of our images by putting them online and allowing people to look at them and tell us what's going on. So we have these websites that you can still go to, where we have the image, users can decide what is in the image, and then they provide all of that information that I talked about us being very interested in. And so with multiple users looking at every single image, we take all of those classifications and extract a consensus answer, and we're able to turn around some very high quality data on a substantially shorter time frame than me. So this has been very, very helpful to us, and it worked really, really well when it was just Snapshot Serengeti and it was just Wild Camgor and Gosa. But if you go online now and Google camera trap citizen science, you scroll through pages and pages and pages of citizen science projects. And we're swamping out our user base. There just aren't enough citizen scientists at the moment to keep up with the volume of data that we're throwing their way. So these projects, they never get completed. We've got projects online that are still processing data from 2 or 3 years ago. And this impedes our ability to use this data adaptively, especially for those projects who need this data for conservation, who need it for adaptive management, who need it to study what happens after an environmental or an anthropogenic perturbation. If we're back in the months to years period for turning this data around, that's just simply unacceptable. Like the citizen scientists alone at this point, they just can't keep up. So this is, of course, where we're turning to you. I can't stress how valuable these camera trap data are and how easy they are for ecologists to collect. And it's really this classification step, this bottleneck, which is slowing down a lot of forward progress in ecology and conservation. So one of the great things that working with these citizen scientists for so many years that they've produced is a massive labeled image library. So it's tens of thousands, hundreds of thousands of images where we know what is in the image, how many things are in the image, and what they're doing. And so this appears to be a very valuable resource for the machine learning community for training these different kinds of algorithms. And so what we're really hoping for as biologists is that by partnering with people who do machine learning and artificial intelligence, that we can get that classification time down again from months into minutes. That's my dream, right? And again, just to reiterate for one final time, the amount of time it takes us to classify this data is just unacceptable. In today's changing world, we can't wait for 2 years to look at the effect of a predator interaction or to assess the effect of a cyclone. There's such a strong need for us right now to find a way to be able to access these data now. So now I'm going to turn the conversation over to Stig, who's going to talk about how computing is going to change the future of camera trapping and conservation.
My microphone. Oh, here we go. Thank you, Meredith. Great. So my name is Stig. I work at DeepMind in London, and I'm going to give you an overview of an approach we took to applying ML to this domain. So the outline of my talk, first I'll cover a bit more detail about the dataset itself and how we ingested that into our pipeline. A hackathon project we did at DeepMind, some examples of working with real-world data and the architecture we employed during our hackathon, and then a little bit of information about how we then attempted to deploy this, and I'm going to try and draw some conclusions at the end. Right, so the dataset itself was something we came across about the end of last year. It looked really, really interesting. It's huge. There are literally millions of photos in this dataset, and all labeled. And however, there's about 6 terabytes of it. And it was hosted on this university server in the US. And with the sort of bandwidth limitations available, we worked out it would take months to download this. So, fortunately, Meredith put her email address on the web page that hosted this, so I got in touch with her, and she responded very quickly and offered to, if we could send the hard disk, to fill this up and send it in the post course. So that was sort of our high bandwidth, acceptable latency solution to the problem. Cool. A little bit more detail about the dataset itself. So it's 225 cameras that have been placed in the Serengeti National Park. And these millions of photos are now available, and they've been labeled by this citizen science community, so that we now have classes and counts for 48 different species in the environment. There's also this particular class, the no species class, for what camera trappers or ecologists call blanks. So because the camera traps trigger when there's motion or changes in heat, you'll get quite a few sort of misfires. So in this particular data set, about 80% of the images have no species in them, at least that we could see. So any sort of system you employ to help you with this domain will have to take that into account. So I wanted to define what we call a capture event. So a capture event is when the camera is triggered. It's sort of programmed, the camera is programmed to take several images in short succession, typically around 3, sometimes fewer, sometimes more. They have high resolution. So the rather distracting example there on the right is one of these capture events with 3 images. The resolution is 2048 by 1536 pixels. So that's really good. And along with each capture event, there is the number of species spotted in there, the list of species names, the count of each species, the site ID, which is the ID of the location of the individual camera, and as well as sort of latitude and longitude of where the photos were taken and the time they were taken. And you can use this information to look up other data like elevation of the terrain and weather data, which might help the model as well. So those are some thoughts we had around it. But since we started working on it, there's constantly more data becoming available, including quite recently some bounding box data has been released. So you can use this for maybe train some sort of image segmentation model. But that's only available for a relatively small amount of capture events so far. So to get this sort of compatible with our workflows, DeepMind, we started on the data ingestion. For this, we used Apache Beam, which I have really enjoyed working with. It's a big open source project. On the Apache Foundation, it makes it really easy to do things like big workflows of any kind of data management. It has these nice abstractions, so you can very easily define each task you want in a workflow. So we use that to crop and rescale images to something that was a bit more amenable for our models. So we reduced the size of each image to 341 by 256 pixels, just so our models have a better chance of fitting in memory. And we went through and made sure there was a consistent set of features available for each example as well. so that the model, once you come to train it, can deal with each example in a consistent way. And this is all saved in a format ready for sampling with TensorFlow. Cool. So now and again at DeepMind we have these hackathons where we take a week or so out of our normal schedule to work on something completely different. So I pitched this project there a while ago, and I managed to collect these wonderful people to help me do this. It's quite a multidisciplinary team. It consists of research scientists, research engineers, software engineers, and ecologists, and actually an optometrist as well. So we thought we'd have a go at this. The thing we all had in common was that we were passionate for conservation. So we had a really close look at the data then. So this is sort of to illustrate the class imbalance of the data. So of the 1.2 or so million capture events, you can see the vast majority are in this no species class. Then we have about 100,000 wildebeest and even fewer zebras, and it very quickly dwarfs. So I've drawn a log plot of this to make it a little bit easier to see. But even on a log plot, it's quite alarming to see. So very quickly does it sort of drastically reduce all the way down to the rarest species, which is Wylla, which we had about 30 examples of. So this is something we had to take into account in approaching this. We also did some analysis on whether there was some sort of correlation between time the different species were seen. So here you see these plots where on the x-axis you have the week of the year or the time of the year, and on the y-axis you have the time of the day, and then occurrences in the data for those. So on the left you can see the wildebeest sort of goes somewhere around July, August. Apparently some sort of migration going on. And hippos don't seem to come out during the daytime. So we learned some biology there as well. And we did this for all the species, and I think this really nicely illustrates really how rare some of the species are compared to others in the dataset. Okay, and because this is real-world data, it's not all like completely curated. So I wanted to give you some examples of things we saw in the dataset. So it would be amazing if every single photo was like this, well-lit conditions, a good distance from the camera, the animal almost posing for the camera to maybe try and get on a social network, I'm not sure. But in reality, a lot of the pictures, this is a particularly bad one, I must say. Some of them look like this, where it's sort of very hard to see what's going on. Some look like this, there's very little lighting. I don't even think the projector can pick it up here. And some have this saturation of colors in this rectangle in the middle. I think this turned out to be a defect in the cameras that Meredith later managed to sort of get a software patch for. So a lot of data like that. There's another example of that. Oh yeah, and sometimes somebody decides to fly their hot air balloon through your area where you're trying to study. I don't know. So the architecture we used during this 5-day hackathon, we started with something really simple off the shelf, ResNet, where we fed just the first image of each capture event to get the logics out of. Then we expanded this to sort of have 3 read heads, if you like, where we then get multiple activations that we combine with a pooling function. And then we started feeding the side inputs, so things like the side ID, just in case the model can glean something from knowing which particular camera did the work. And things like the time of day, we even fed weather data and humidity, elevation, and that kind of thing to it. For example, some of our advisors said that some animals' occurrence really depends on how close they are to waterways, so location could be really important for that. So we tried throwing all this data at it, and the side input went through a fully connected network, and then combined all of these activations using a linear layer and read the logics out of that. So at the end of the week, we had something that we were pretty pleased with. So the audience wants to compete with our model. Hopefully you can all see that there are zebras available in this one. And here our model correctly says that we have wildebeest. At least I hope it's correct. Yay, good. And here is one of these many no species examples. Cool. So we sort of realized that it's all good to have this working in a lab in London, but what really counts is getting it out there and working in the field. So we started talking to Meredith about how we could deploy this, and Meredith got us in touch with the Grumeti Fund. So this is a charity that works in Grumeti. So Grumeti is a national park adjacent to the Serengeti, where all the images were collected. It's part of this whole Serengeti Mara ecosystem that spans Tanzania and Kenya. So in theory, there should be a very similar landscape, very similar set of species going around here. But of course, our model had been trained on a very different set, so we were keeping fingers crossed that we'd be able to transfer enough knowledge that it could be useful in this other location. We started talking to the researchers there on requirements, and this is the list we came up with. So of course it has to run in the wild, because a lot of the time would otherwise go with getting all these masses of data onto the internet. That I understand that can take several months. You have to go to the nearest hotel or university, or sometimes just put it on a hard disk for the next person going out of the country. So you can go to somewhere like the States and upload it to citizen science websites there. So we wanted to shortcut that whole thing by having it run there in the field. So it had to run modest hardware requirements. We didn't have a data center available there, and there would be no promise of a reliable internet connection. And ideally, I think my microphone's still. Here we go. Ideally, it should work on Windows, which is the operating system that most of the researchers out there are most comfortable with, and ideally with a graphical user interface, because most of them haven't used the command line that much. And there was this requirement as well to, if you run it several times, you don't want to spend time predicting things you've already processed, so it has to keep track of that. And it also had to be pretty fast. We sort of estimate the workload will be around 55,000 images per week that are coming into the system. And of course, at the end, it would have to output some summary statistics, like a CVS file, a bit like the one Meredith showed us in the spreadsheet earlier, with all the data that the model has predicted. So we came across this way of hosting a pre-trained model using what is called TensorFlow serving. Some of you might have come across. So you can save your TensorFlow model in the save model format. It saves the model along with its weights. And then you can run it inside a Docker container. So it'll basically run on anything that can run Docker, which is almost all operating systems. It'll spin up a web server, and you can speak to this web server via HTTP. And we decided to write a Python client to speak to that server. Our whole software design looked like this. So the client would, by the user, be pointed to a folder on disk of arbitrarily organized images, so any sort of folder hierarchy there you can imagine. It would then group these into capture events by looking at the sort of exit data and timestamps of each JPEG, and transform these images into something that the model would expect in terms of resolution. And it would then group them into these capture events of 1, 2, or 3. So if there were fewer than 3 images found in close succession in time, we used like a 5-second threshold. It would pad with sort of blank data, and if there were more, it would truncate. And then it would batch these to the batch size used by our model, feed all this into the TensorFlow serving system in Docker, and output predictions. So we thought, okay, let's go and see if this works. So last week, actually, these are pictures from last week, we brought our prototype to Tanzania, and had a look there. The first time I've been on a site like this, we found lots of data around there. So this is just like a very small subset of the huge data set they're constantly collecting. A whole bunch of memory cards come straight from the cameras there. And we spent several hours getting the machine set up there, getting the right sort of upgrades for software and everything on there. And by the end of the couple of days there, we had something that worked really well, that we were really happy with. So let me draw some conclusions. So the results we ended up with after this have high classification, precision, and recall for most of the species, certainly not all yet. In fact, the prototype we brought out, we're only happy with running as binary classification for now. So it can say which ones are blanks and which ones have animals in them, but that still removes like an 80% of the workload. We're getting quite close in some of the more abundant species in having sufficiently high precision there as well. And we're doing various things now to try and improve that. The model also puts out these confidence estimates so that if you're looking at it, if it says it suddenly found a really rare species, you can at least get like a feel for what the confidence of the model is for that. If that's something you can rely on, you need to go and look into it further. So maybe you can take some of the sort of least confident predictions and bring them onto citizen science, but at least with a much lower workload. And we calibrated this confidence using sort of temperature scaling to make sure that it sort of gave a reliable prediction for each for this data set. So this has resulted in a really big reduction in the manual workload, as well as a huge reduction in the time taken between capture event being taken and the final analysis. And hopefully it will speed up ecology research and conservation management. In terms of next steps, so as I said, we want to improve the precision recall, and we're also experimenting with a completely new approach for counting in DeepMind. Since we did this hackathon, a few more people at DeepMind got interested, including our vision team and others. So I'm hoping to be able to share. There's a fly. Doesn't want to be classified, maybe. We're hoping to be able to share some of this research later in the year with all of you. And lastly, I just want to end with a thought that something I feel quite strongly about. It feels a little bit silly that a group of people in London are trying to solve these problems, hundreds of kilometers away from where it's all taking place. So if this idea, or you already have similar ideas for this, if this has inspired you, please get in touch, and we'd love to exchange ideas with you. We have some contact information here, along with a link to the data set we used. It's publicly available, and there's a link there at the bottom to a paper that describes the data in a lot of detail. Thank you very much. So I think we have plenty of time for questions, if there are any.
Thank you for a nice talk, or actually for two nice talks. My question is about whether there are similar projects, because this project focuses on animals, let's say, on mammals and maybe birds. But what about animals of a smaller scale, like snakes, insects, or maybe even smaller scales, like microbees?
Well, we definitely have camera trap data on smaller species because of their small heat signatures, and like with reptiles, the difference in heat signature is not so great from their backgrounds that we don't have as many images of those kinds of animals. I do work with a camera trapping project in the States that did end up with a lot of pictures of insects. From an ecological point of view, we haven't had anyone clamoring for that data yet. So getting that data processed hasn't been the top of my to-do list, but I assume it would be possible through the same kinds of methods.
Yes, and one really interesting question there to me is whether would you need to train a model for each kind of ecosystem or biome, or will you be able to train models that will sort of bring all of this together and have one general model you can inquire for these predictions?
Thank you.
Hi. Cool. So I think a question I had, so you mentioned, we alluded to the fact that there is also there's also satellite imagery and drone imagery. I think one of the questions is, how is that also publicly available? And then you also mentioned a lot of like ancillary data, for example, weather, temperature. I've worked on a couple of projects where it seemed incredibly difficult to get any kind of weather data at a sort of kind of a granular time scale. It's like, yeah, for this month, this is the average temperature. That's not really useful when it comes to all these more sophisticated kind of models. So I think it's more from a data acquisition perspective. How can we gain ecological data from the different sorts of biological sort of biomes?
Yeah, well, so for example, the satellite and the drone data at the Serengeti site where I work, we do have a couple of people who've tried in the past to get that imagery. and it's difficult and it's expensive, and the government doesn't want to necessarily release it. Drones are now banned in Serengeti National Park, so you can't gather that kind of imagery at the moment without incredibly special permits. So those kinds of data, I do know researchers who are trying to obtain that data, and they're using that data because you can count animals from that data. You can look at how animals move across landscapes from that data. So it's good data, but you're entirely right that it's very difficult for us to access. So camera trapping, we produce that data ourselves. We don't rely on other sources to give us that data, which is one of the advantages of camera trapping. In terms of the environmental covariance that you would want, what we want for our ecology as well, I think that's driven very strongly by the researchers on the ground and what their what interests are and what capacity they have. So many sites I work at, we do collect rainfall data and daily temperature data, and we have weather sensors, but not every site has that data. Not every site has the capacity to collect that data. So I think if you were interested in working with a site that had some form of image data, liaising with the researchers on the ground ASAP and suggesting that those would be valuable information to start collecting would probably be your best bet. Because I've done the same thing. I've looked online, where do I get sunrise, sunset data for Serengeti? Where do I get cloud cover data for Mozambique? Where do I get daily temperature data for Zimbabwe? And those kinds of data, I think it's very hit or miss. So I think you hit on some really key limitations we have. So we're working right now with the data that we can get, and I think the best data is the data we generate ourselves. Does that answer your question?
Hi guys, thanks for the talk. It was really cool. So I guess my question is a bit more about funding. So like animals can't herd fund the solution, or crowdsource the solution. So considering a lot of governments in Africa have a really limited budget, going into conservation, and considering that this is kind of the responsibility of the human race as a whole, do you think corporations like IBM, Google, DeepMind are kind of doing enough in that space with funding and research? Because you mentioned that they started this hackathon, which is really cool, but why not upscale it and make it a lot bigger of a priority for corporations and working with governments as well?
Yeah, so I really think we should do more to sort of enable this kind of technology to become available. So what I would love to see is once we're done with this research, we open source everything, and people can take it further and get even more out of it. In terms of the cost of training something like what we did, it was actually relatively modest. You can run on one GPU overnight and train on this whole data set. So I don't think it's completely inaccessible. It's not like you need to have a data center to do this kind of thing. So that's really encouraging, I think. So, as long as you have a little bit of cloud access, I think this is doable. And in terms of deploying it, that really depends on the site you're deploying it at, I think. But I think there are workarounds for this. I think we just tried everything we could to try and get it out there. And I think if everyone tries that, there's definitely possibilities there.
If I could chime in on that as well. We do have this very large labeled image library, right? So I get a lot of people asking me all the time. I think more computer scientists have requested our labeled data than actual ecologists have to build all kinds of different neural networks and algorithm things. But the thing that's been so frustrating for me as an ecologist is someone will take my data, they'll scoop it up, they'll disappear, they'll build some kind of fancy architecture, and they'll publish a paper on it, and then they're gone, and I never see them again, and I have no idea how to implement their fancy architecture. I don't know what do I run that on? How do I download that? How do I access what they've built? And so the thing that's been just really super about working with DeepMind is that they've actually created a product that someone like me, who chases animals all day and grubs around in the dirt and has a Windows computer, that I can use and that I can share with my teams and that is actually coming back and returning and making, like contributing back to the original source and actually making that difference. Because I do appreciate that people want to use this data to do amazing theoretical things, but I would really like it if that could then, continue to help us with the problems that we have with our data in the first place.
Thanks.
Hello. Which animal species? Sorry, over here. Which animal species have lower precision and recall, and why do you think that is?
So that it's highly correlated with the occurrence in the dataset. So we need to look at ways of sort of addressing that data imbalance. It would also be cool to do further studies on that to see whether there's maybe an animal size factor or distance from the camera, those kinds of things. There's a lot more analysis that can be done in this area.
Hi, thanks for the cool talk. I was wondering if you guys know about the iNaturalist collection of images of wildlife, and then the workshop that you're organizing here at CBPR. So they have a workshop every year for the last 3 years, I think, and they also organize Scavenger Challenge. So they're saying by now, over these 3 years, they've collected quite a lot of different solutions that people suggested in the Scavenger Challenges, but also they have a lot of labeled images. So I was wondering if you tried to look at, combining maybe your data with their data, because I think it's also open and still accessible, maybe using some of the suggested solutions that people proposed in these challenges, and maybe organizing your own kind of challenge as a way sort of to get the solution in the form that you will be able to use later. So like, put the requirement of Dockerization and providing all the documentation and all the scripts to run that stuff. So what exactly, to guarantee exactly what you're talking about is that when the competition is over, the project is over, you still can keep reusing those things.
Yeah, I'm a huge fan of Kaggle. In fact, one of the participants on our hackathon team used to do Kaggle competitions all the time, and he won some big ones to do with recognizing whales, and then that got him a job at DeepMind, which is good for me because then he could help me with this project. But yeah, I think that's a really good idea. Like if we can take some of these data sets and particular problems and present them on something like the Kaggle platform, that'd be really good. There's also the new Zindi platform that is specifically for the African continent. I think that would be a very appropriate sort of forum for doing this. So maybe you can bypass DeepMind next time and just go straight to this.
Straight to the source. Well, in terms of the additional data sets that you were talking about, so where we host our camera trap data is a repository called Wylla, which is labeled image library of something or other. But they also have several other labeled camera trap data sets that are available for download. I think they're mostly from North American camera trapping projects. They're all a little bit smaller than ours, but they're there, and I know some people have used our data and their data and tried to do transfer learning to see if they can improve different algorithms. iNaturalist, as I understand it, is an app where you take pictures of nature and they join a cloud repository. So I'm not certain how different those images are than the camera trap images, but that's also a really wonderful image database, a really great citizen science project for those of you who want to dip a toe into ecology. Yeah, no, they're a wonderful repository of images that I know I haven't looked into enough.
Thank you.
Hi, I'm Sim. Thank you for your talk. This is very relevant to me. My honors project is about this. I'm just curious, how did you deal with the imbalance in the data set? Did you use data augmentation? What type of data augmentation?
Yes, we tried quite a few different things. It's a whole list of things that didn't work very well. But what we still have in our pipeline is data augmentation, where we slightly rotate the images and change the colors a little bit. We also tried things like combining colors, but mostly these random perturbations to give us extra samples. We have a few other things on our to-do list that we want to try in this area. Things like when you put your bats together, if you base that on how good precision recall you already have for certain classes and try to remove things that you already know well, then maybe that's another way to sort of keep adding knowledge to your model.
Hi, my name name's Meredith. I'm from Cape Town in South Africa. And so, firstly, thank you so much for the amazing work you're doing in ecology in Africa. And this is just a thought I'm having out loud. Has it been considered to maybe extend a project like this? And I don't know how it would be done, but maybe machine learning for sea life conservation, maybe in a marine biology context. In South Africa, we have whale watching in Cape Town that happens quite often, and I just recently became aware of the great white shark populations seemingly disappearing in Cape Town's waters, and especially in the wake of Japan reinstating whale hunting. I'm really happy about the work for ecology on the ground and all sort of like terrestrial ecology, but what about the sea, which is 70% of the globe? Just a thought out loud. Just a future work section at the end of a thesis.
Do you have thoughts on this?
I do. So, yes, exactly. This is a very terrestrial-based data set here. I can't speak to how machine learning is interacting with that community, but the citizen science community has a number of different projects focused on sea life, both along the shores, Arctic bird sea life, classifying images of whales from drones. So if you go onto the citizen science platform, there's no link. Oh, there's a link. No, there's no link.
No,
there's no link. Okay. The citizen science platform that I use to host our camera trapping data is called the Zooniverse. And if you go to the Zooniverse and you look through their ecology, science, nature section, you'll see that there are a number of projects that different researchers around the world are doing, where they are crowdsourcing the data that they have in order to get those various kinds of data processed. And I understand that that's both users looking at collected image data, users collecting data themselves, like through the iNaturalist app, like snapping pictures with their phones, also acoustic analyses of underwater whale calls and things like that. So I know there's a lot of data out there. There's ways that people can help move that data along, but I don't know if people in the machine learning world have tackled any of that so far.
I think there are definitely a lot of these out there, and we quite frequently have people contact us. Someone just recently contacted us to see if we could help count penguins in Antarctica. So I think what I really want to do, I really want to get this current system working really, really well first, and almost use that as a proof of concept that it can make this work, and then share these ideas with everyone else to help solve them, because we can't solve everything in an 8-man team or 8-person team, but it'd be nice if communities across the planet will pick up these kind of ideas and contribute their own ideas. I'm quite excited to see what comes out of the hackathon we've been running here this week. We'll see the results tomorrow, and I'm sure there'll be some great ideas there we can also incorporate into this.
Hi, so another question. A little while ago, I read a paper from NVIDIA where they released basically using GPUs to render images and using those images as a purpose for classification. And particularly, these images are created for recreation. The level of graphics that often computer games can sort of create, you get almost like real-life simulation at times. Would it be possible to almost recreate the environment of a biome that you are currently studying, where you would have a model reconstruction of an animal, obviously a very rare animal, walking around different sort of manners and basically use it for learning purposes? Is that something one could possibly do?
So if I get your right, you're thinking of creating like a really high detail simulation, which you can then sort of take photos from in a similar way that a camera trap would in real life. Yeah, I think you would need particularly good simulations for that. A lot of what I think, I'm definitely not an ML expert, but from what I gather, the statistics of the input data needs to be completely consistent for this to generalize. And I think something like that would be very hard to get the exact lighting and everything right for. Maybe what you could try instead is to train a generative model on this data set and then generate new samples that way. I think that might be a simpler way. Then you don't have to write a full simulation either.
Thank you very much. So my question is on wild. So what is some of the design considerations for deployment? Because we're using TensorFlow serving on device, or was it feeding to a remote cloud? And also, how did you deal with the problem of internet barrier in the Serengeti? Thank you.
So the bandwidth issue in Serengeti we got around by getting things on hard disk and shipped around for training purposes. So that's sort of an upfront, I guess, time cost. Once you have that, you can pre-train the model in the cloud and deploy it, and then you don't need internet at all in the field. So you could do similar approaches to other areas. Okay, I think that's all. Oh, there's one last question here.
So I was wondering what are the kinds of patterns you're hoping to extract, or maybe you extracted already, and how does it link to conservation? Like, what are the immediate actions you could take from these patterns?
So you mean what are the ecological patterns that we're looking at?
Exactly. So maybe tracking.
Yeah, so I mean that's a huge question, because again, I'm working across so many different sites, and each site has its own research directive. But some of the basic things we do is we use the camera trap imagery first to establish animal population trends. So how many animals do we have of each species, and how does that change through time? So we can track these how animals respond at a population level to different kinds of perturbations. But those perturbations might be a drought, it might be supplemental feeding, it might be fencing of the reserve, it might be a new community was established on the border, it might be poaching has increased, it might be we tried to do something to decrease poaching, it might be we reintroduced wild dogs, it might be we reintroduced herbivores. So, like again, understanding populations and trends through time is important for a variety of different reasons. I study animal behavior, so I'm very interested in how animals move through landscapes. And again, with this large spatial coverage with our camera trap grids, we're able to look at migrations. We're able to look at how animals move in and out of reserves. Say, if you have elephants that are going to go raid some crops and then come back, so we can identify which elephants those are. We can look at how animals move relative to resources as resources change through time. Whether that change through time is through the seasons as they become more and more scarce as rainfall changes, or across years where we have El Nino years, we have years with lots of rain, we have droughts, we have years with extreme weather events. I focus a lot on predator-prey interactions, so I look at the sort of shell game between how prey move to avoid predators and how predators change their landscape use to avoid prey, and then how prey respond to that, and how that changes with things like lighting conditions. Lions hunt better at certain parts of the lunar cycle, how it changes when the migration is present, when you have a lot more food than you might otherwise. So the questions are a very, very mixed bag. But like I said in my part of the talk, I think it really comes down to understanding animal populations, their distributions. And then the behaviors is actually really fun, because I think distribution and behavior is sort of the same thing, like where animals move and how they use a landscape. And I'm on my soapbox right now, so someone needs to cut me off. But the behaviors are fun, and this is something that I think is going to, that we might kind of miss out on relying on machine learning. So with our citizen scientists, people look at the images, and like human brains look at these images, and if there's something weird, a human brain will pick that up as weird and will flag that, and that's how we've actually made some very interesting scientific discoveries. So we had a paper come out 2 years ago where some of our citizen scientists had flagged images of oxpeckers roosting at night in the armpits of giraffes, because they're like trees, but they're warm, I guess. That's great. So like we've been making some very interesting behavioral discoveries as well from these camera trap image data. So if you could get the algorithm to do that too.
That's inspiration for the audience. Like, that's a research paper just there to try and pick up these anomalies.
Birds in armpits,
yeah.
That needs to be. So I'm sorry I can't give you, if we wanted to talk about a specific site, I could go into more detail about the research that's going on the ground. But the really brilliant thing about using camera trap data is it's not like we're putting 6 collars on 6 wildebeest and then we know some things about 6 wildebeest. We're deploying 60 cameras and now we know so many things about so many individuals of so many species, and with the right kinds of environmental covariates and the right kinds of information about how humans use these spaces as well, the number of questions we can ask is essentially limitless. Off the soapbox.
All right. Well, thank you, everyone.